So in the last few videos, we've been looking at redox, and we've been looking at balancing redox equations. And the question is, why are we doing this? And it turns out the answer is really amazing, and that is we can generate electricity through redox equations. So, for instance, if we take zinc and copper ions in the form of copper 2, they can react and they can form zinc ions and copper. And this is a redox equation because if you assign oxidation states, you can see the zinc has increased and the copper has decreased. We know that the zinc has lost 2 electrons and the copper has gained 2 electrons. So essentially the electrons have moved from the zinc to the copper. So loss of electrons is oxidation, gain of electrons is reduction. And if you remember oil rig, oxidation is loss, reduction is gain. That should all come back to you. Now, the problem with these electrons is that when we mix zinc and copper ions together, they just react straight away. The electrons hop from the zinc to the copper. And it turns out that's not cool. And the reason that's not cool is because we want those electrons to do some work, right? And so if the electrons just come out of the zinc and directly jump onto the copper ions, and zinc ions can dissolve in solution, we haven't used our electrons. We've wasted a lot of energy here. By letting the electrons directly go from one to the other, right, we're not taking our cut. So think of the tax man, right? We have to make sure that when money changes hands, we have a record of that transaction so we can tax it and pay for roads and schools and libraries and things like that. So the answer to our problem of how do we use and tax this electron's energy is to separate out the reactants into what we call a voltaic cell. So we're going to build ourselves a voltaic cell, which is sometimes called a galvanic cell, by the way. And here's what we do. So first off, we have to separate the zinc from the copper. And the way we're going to do that is we're going to take a strip of zinc, and we're going to call this an electrode. And we're going to dip it in a solution containing zinc ions. So some zinc nitrate might perhaps work. And what's going to happen here is that this is going to separate off. So the half reactions literally appear in one half versus the other half of our setup here. So the zinc is going to lose 2 electrons. Okay, now where are those electrons going to go? And the answer is they've got to go to the copper. So they are going to be transmitted along a wire. Okay, we're actually going to go ahead and extend this wire out. Now, in order to measure the energy of those electrons moving through the wire, we're going to hook up a voltmeter. And the voltmeter basically tells us how much energy the electron is carrying as it moves from one side of the cell to the other. All right, so now we got to get it to the other thing. So we're going to take a copper sheet, a copper electrode, and we are going to immerse it in a solution of the copper 2 ion. And what's going to go on here at this electrode is the copper 2 ion can react with those electrons coming down the wire. So those electrons are coming down, right? And they are able to essentially come out like so and jump on the copper ions and turn it into copper atoms. And so those copper atoms will literally just build up on the surface of the electrode and just add to it. And of course, if the zinc is dissolving, then you will find that the zinc will kind of slowly degrade away and disappear like so. So there you go. That's my very, very poor drawing. Now, it turns out that when you do this, nothing actually happens after a fraction of a second. And the reason for that is that when the zinc ions are formed in the left-hand beaker, the left-hand beaker gets a positive charge. And when the copper ions are removed from the right-hand beaker, because you remove a positive copper, you end up creating a negative charge. And that negative charge that you build up there, if you like, will repel electrons from coming down. And also the positive charge you build up here will attract those electrons back. So what you find is that after you've made a little positive charge here, the electrons can't escape. And after you've built up a negative charge here, the electrons can no longer come down. They're repelled. So this is a major problem here. And we've got a solution to this. And the solution to this is we're going to use what we call a salt bridge. And the salt bridge is literally a bridge or a glass tube. I guess a bridge maybe is literally not literally what I mean. And sorry about that. So this is our salt bridge. And the salt bridge allows these solutions to retain a neutral charge. So I'm going to put some cotton wool at the end just to prevent mixing. So some cotton wool or whatever it may be, glass fiber or glass fritz or something. And I'm going to fill it with an ionic compound. And we typically fill it with something like potassium nitrate or potassium chloride. Potassium and nitrate are neutral. And what it's going to do is if this solution here is becoming more and more positive, then I can take the nitrate ions out and of the salt bridge and let them enter the solution to keep them neutral. So my nitrate is going to migrate into here and keep it nice and neutral. Now, the right-hand beaker is getting a negative charge, and I'm going to neutralize that charge by taking the potassium ions, the K+, and essentially allow them to move out of the salt bridge into the solution. And so it's going to keep the solutions nice and neutral. So that charge buildup is going to go away. So again, just to kind of emphasize here, if this is the salt bridge and it contains potassium nitrate, those ions can migrate out of the salt bridge into the solutions to neutralize them. So these negative charges here will help neutralize the positive charge buildup over here and vice versa. So that is going to be the trick. So the V at the top we said was our voltmeter, and the voltmeter essentially measures the energy the electrons are moving with, and it measures it in terms of a voltage. So when we say 1 volt or 2 volt or 3 volts, we're really talking about the energy the electrons have moving from one side to the other. More properly, it's a difference in energy. It's a potential difference. So the electrons have potential energy, and we're measuring the difference in potential energy. So the electrons on one side might have a higher energy than the electrons on the other. And so as they fall down from one electrode to the other, right, that gap there is how much energy that they're moving with. So the analogy, if you like, it's analogous to water pressure. So think of a waterfall, and the water falling creates a pressure. Or if you like, the bigger the difference in energies between one side and the other, the more pressure an electric hose is filled with, if you think of a garden hose. It's a very interesting kind of analogy. In the old days, we called it very crustily an electromotive force. I can't spell. Electromotive force, or EMF. So we no longer refer to it. It's not really a force so much as an energy difference, although we'll see that energy and forces are related to each other in physics. But you'll still often hear it called electromotive force, or potential difference, or just voltage. So I'll refer to it probably as cell voltage, just because I think that's a much easier way to refer to things and keep track of things. One more little bit of terminology, and then we'll end this video, and that is that the zinc is being oxidized, and this process occurs at what we call the anode. The copper is being reduced, and this process occurs in a cell at the part we call the cathode. And so the cathode is just the name given to the part of the cell that reduction takes place in, and the anode is the name given to the part of the cell that oxidation takes place in. So this whole thing here would be the anode, this whole thing would be the cathode. Some people just refer to the electrode itself as the cathode or the anode, and that's totally fine too. And I'll offer you up one way to possibly remember it, and that is you can have an ox and a red cat. And I don't know why, but an ox and a red cat is an easy way to remember. Anodes are oxidation and reduction is cathode. So there you go.